So we're going to answer a chemical kinetics tutorial sheet. So this is like the fourth tutorial sheet I'm answering and uploading. So we have quite a number of questions that we're going to go over. So as you can see, question 1, here we're going to determine the average rate of decomposition. Applies to question 2 as well. We have question 3, which deals with reaction orders given the initial rates. And then we're also given the rate of formations for question 4 as well. We'll apply the same concept. So that's still question 4. And then of course we've got a part for the reaction mechanisms. We've got a different kind of a question, but asking us to determine again the lateral. Question 6 is where they've given us the initial rates and then they want us to find x and y. Question 7, they want us to determine the rate of formation in relation to a reactant. And then we have got question 8, got question 9 and 10, question 11, question 12, question 13, 14, 15, 16, 17, 18, 19. So these are the questions that we're going to answer in this video. Okay. So link in the description to the actual full video. Okay, so I'm going to answer a few questions just here. So what is the average rate of decomposition of A to B by the reaction? So one thing that you should know, in my introduction to chemical kinetics, I explained to say that the rate is given by the, if you're talking about the reactants, it's negative 1 over the stoichiometric coefficient. In this case, we're talking about that reactant, so it's a 2 there, so it will be over 2. Change in the concentration, as we are told, change in the concentration divided by the time it took. So that's going to be our formula. So all we just have to do is just substitute the information that has been given to us. So for the change in concentration on top, what do we have? So the final concentration, since we are trying to focus between 600 seconds and 1200, so the final one was 0.93 times 10 to the power negative 2. That was our final. And then minus the initial, which was 1.24 times 10 to the power negative 2. Divided by the change in time, right? So for the change in time, that was from 600 seconds to 1200. So we have 1200 minus 600 seconds. So don't forget that on top we've got concentration, so molar concentration over time, seconds, right? So you can see that the units match up to a rate. So if you're going to subtract what we have on top, grab your calculator, 0.93 times 10 to the power negative 2 minus 1.24 times 10 to the power negative 2, that will give you a negative, divided by a difference there is going to be a 600, and then multiply by negative half. So the answer I'm getting is 2.58 times 10 to the power negative 6 molar per second. So what is the rate? So a rate is change in concentration over the time it took. Of course, don't forget to multiply by the stoichiometric coefficient. So the reason why we add the negative there is to ensure that every time we are determining the rate, it should always be positive. Okay. If we were focusing on the rate of formation of A and B, we could have used a positive instead, because we know that the final, in terms of the products, is higher than the initial. Why is it that for the reactants the final is less than the initial? It's because as the reaction progresses, as we saw from 600 seconds to 1200 seconds, that was a reduction. There was a reduction because reactants react and so they reduce in amounts. Same concept applies to question 2. We want us to determine the rate. Whatever it told us, they've told us we've been given information. What are we told? So that is the equation we are given. Iodide ion is oxidized by hypochlorite ion in basic solution. Okay, the equation has been given there. Okay, and then in 1 molar concentration of sodium hydroxide, the iodide concentration, so the iodide ion concentration was equal to the the hypochlorite ion. Okay, so and then we are told the time. It was from 2 seconds to 8 seconds. They observed a change in the concentration. Okay, so calculate the average rate of reaction of iodide during this time interval. Okay, so what this information is about, what is about iodide ion, as you can see. So if we look at iodide ion in that equation, it's having a stoichiometric coefficient of 1. So in terms of the rate, which is the average rate, of course, because we are looking at it as the range of time, that's going to be -1/1 change in the iodide concentration divided by the change in time as well, just as like we did in the question before. So therefore we have -1. Change in the iodide concentration would be 0.00201 minus 0.00269, and then of course divided by the time difference, that was 8 minus 2. So for the top part that's smaller, this is seconds. So grab your calculator there. So -1 times 0.00, first of all you can start with what is in the brackets, 0.00201 minus 0.00269. So realize that the other part is bigger, so it is going to be negative, divided by the difference, which is like a 6, and then multiplied by the -1, it becomes a positive result. So I'm getting 1.13 times 10 to the power -4 molar second. Okay, that's it for question 2. You can see that there's actually no difference between question 1 and question 2. They are all based on the same concept. Okay, so we're now on question 3. Question 3, we are given a table. So the question says iodide ion is oxidized in acidic solution. Maybe let me zoom in a bit so that you can see clearly. So iodide ion is oxidized in acidic solution to triiodide ion by hydrogen peroxide. A series of 4 experiments was run at different concentrations, and the initial rates of I3 formation were determined. So from these data, obtain the reaction orders with respect to the three different reactants we are given. Okay, so you know that most of the questions, if you've watched some of the videos, most of the questions we've answered before basically get to focus on the idea of 2 different reactants. Now in this case it was a unique because we have got 3 of them. So reactant 1, 2 and 3, and then they want us to find the reaction orders. How do we go about it? So let's basically handle it. So just like we do in the other kind of questions, we have to observe experiments where 2 of the other reactants are going to be the same. Okay, before that, let's come up with a formula for the electro. So the electro is expected to be R, denoting the rate to be K, multiplied by the concentration of all the reactants. Okay, iodide, and then H plus. Now all these are supposed to be raised to certain powers, so we'll call them X, Y, and Z. Let's call them that. So let's try to identify the experiments where we can see that any 2 are constant. So if I look at experiment 1 and 2, I can see that iodide is constant, so is hydrogen ion, but the other one was what? Was changing. So we can start with that one. So where do we have bigger values? I can see that in the second one the values are bigger. So we'll start by the rate, since the equation starts with the rate. So we have 2.30. I'm going to be substituting in this equation that I've come up with. 2.3 times 10 to the power -6 is equal to K. Now you can see that first of all we've got H2O2. So I've actually arranged them in the same order. So therefore we have 0.02. I'll be removing the last zeros, they're not significant, to the power X and then for iodide it was 0.010 the power y, and then for the hydrogen 0.0005 the power z. Okay, that is for experiment 2. Now we're going to divide by experiment 1. So for the rate for experiment 1, we had 1.15 times 10 to the power negative 6 equal to k, then 0.010 power x, and then we had 0.010 power y, 0.0005 the power z. So you can see that everything else was the same except for this part. So the k and k will divide, this and that will divide, give us 1, that will also divide. That's the actual point. That's why you are basically trying to ensure that you basically get to find cases where the other two are the same. So you realize that if you divide what's on the left, so 1.15 into 2.30, that's going to just give us a 2. Now this time is divided by that. Since we've got the same powers, we can actually group them, divide them, they'll give us a 2. We'll maintain the power, so 2 to the power x. So from indices we know that x therefore becomes 1. So that's a reaction order in respect to the first reactant, so that is a 1. So x is equal to 1. So we can now move. Let's try to identify a different experiment now where you can see that they are the same. So if I look at experiment 1 and 3, you can see that the first reactant is the same, second one was changing, third one is the same. So therefore we can use that one to find the reaction order in respect to the iodide, which was not the same. So we'll divide, of course, experiment 3. Experiment 3, the rate is 2.30 times 10 to the power negative 6 equal to k. Now at this point, as a student, you have to be sharp. At this point you already know that the cases where they are the same, they are automatically going to divide. Okay, so this part will come and divide, so that part come and divide. So we'll just leave out the part which would change. That is for the iodide, that would be 0.020. Now iodide, be careful, is raised to the power y. Okay, divide by the first experiment, 1.15 times 10 to the power negative 6. Equally, we'll just consider the iodide, which was now 0.010 the power y as well. So of course that gives us a 2 on the left. K will of course divide. That will give us now a 2 to the power y again. So you can clearly see that even in this case y still becomes 1. Okay. And then finally we can look for the other case where the other experiment, where the other two, the first two are going to be the same and then the other one may be different. Well, for the third one, it doesn't really matter. Even if you find a case where there's no that case, you can just get any experiment, any two experiments, and then substitute the values of x and y. Okay. Alright, so let's consider if 1 and 4. 1 and 4, you consider that we've got the last one actually changing, yet the first two are the same. So equally here we'll consider just the rate, actually the unique part is the rate are the same. So we'll say 1.15 times 10 to the power negative 6 representing experiment 1. I'll only consider a case which is changing, which is that one. So 0.00050 raised to the power z divided by the second one, or actually the last one, the fourth one. So that would be 1.15 times 10 to the power negative 6 K, and then there it was 0.00100. Okay, so on the left you're going to get a 1 is equal to, now on the right what are you going to have there? So you can clearly see that I've actually done the opposite here. I've put the values that are bigger down, so it's going to be 1 over 2, because that one into there it's 1, there it's 2, so 1 over 2 to the power z. K's are going to cancel out, so this is the same as 1 is equal to, so if you're not comfortable dealing with fractions, put the bigger values on top. So this is going to be 2 to the power negative 1. Whenever we've got a fraction, whenever a number on the bottom goes to the top part, the power changes. If it's a negative, it becomes a positive. If it's a positive, it becomes a negative. Okay. So don't forget our z that is outside there. So therefore, we have 1 equal to 2 to the power negative z. Now 1 on the left, to ensure that we've got the same base, can be expressed as 2 to the power 0, so that we have 2 to the power negative z, and negative z being equal to 0 is thus z equal to 0. So we found the reaction orders in respect to all the three we had here. So obtain the reaction orders in respect to the reactants. There we are. So that is a 1, that is a 1, that is a 0. Find the rate constant. So if they ask for the lateral, it was going to be just the equation we add, now putting in the values. So H2O2 the power 1, and then iodide to the power 1 as well, and then finally H plus to the power 0, which in that case will just be eliminated, so I won't even show it. Now to find the rate constant, how do we go about it? To find the rate constant, we have to substitute in the equation. Okay, just substitute in the equation any value, get any experiment of your choice. Okay, so let me go for experiment 1, right? Let me go for experiment 1. So our rate there was 1.15 times 10 to the power negative 6 for experiment 1. And then our K is what we're trying to find. H2O2 was 0.010. Iodide was also 0.010. So our goal is to find the value of K. So we can divide by the product of the two on both sides. So 0.010 times 0.010. Okay, so that will divide. So 0.010. So multiply what's on the bottom, divide that into what's on top. Our value of K becomes 0.0115. Okay, now it's a good idea to always indicate the units. So if you look at the overall order of the reaction, if you add all the powers, we add 1 plus 1 plus 0 is just 2. So the shortcut I use for finding the units is m to the power 1 minus n s to the power negative 1, where n denotes the overall order. So in this case, the overall order was a 2. So it will be like that. So it will be m negative 1 second negative. So these are the units for the K, and so we found the constant K as well. Okay. Okay, let's look at question 4, which is very interesting. We're told from the data in the table, determine the order of the reaction with respect to OCl, iodide, oxide, hydroxide, and the other order. So equally we've been given 3 reactants, and then we've been given the rate of formation. So we want us to determine the lateral and also determine the value of the rate constant. That's part A. Part B, we are given the mechanism, consistency with a net equation, and of course with the lateral, which is the rate determining step. Is it appropriate to refer to hydroxide as a catalyst in this reaction? So let's first of all answer them in the order they are given. So first of all, let's find the lateral. So in this case, these are assumed to be the reactants that we've been given, right? So we are supposed to find the electron in respect to these three. So if we're going to come up with an equation, we can say let our R be equal to K, and then we have three distinct reactants, okay, as you can see. So now all these are going to be raised to different powers. Let's call them A, B, and C. Okay, so what is our goal? Our goal is to find the powers of the values of A, B, and C. Those are going to be the orders in respect to the reactants, and of course will give us electron. Okay, so equally, if you're able to remember in the other question, we are looking for cases where the other two are going to be constant, right? So which cases? Let's call this one experiment 1, 2, 3, 4, and 5. So if we're going to look at experiment 1 and 3, so the first reactant is different, the other two are the same. So I gave you a tip on how to go about it. How do you go about it? So how you go about that is ignore the ones that are the same and just substitute in the cases where they're different. So which one has got bigger values if you compare 1 and 3? So I can see that 1 has got a bigger value, so I'll go for 1 to be the first one. So substituting in that equation that we have of our electron, the rate is 4.8 for experiment 1 times 10 to the power negative 4, and then equal to K. Then the reactant that is changed was this one. So that was 0.0040. To the power what? That is to the power A. Everything else was the same. So we know if we're going to divide by the other experiment, they're automatically going to divide. So we'll divide by the third experiment now. The rate there was 2.4 times 10 to the power negative 4 equal to K. And then of course for the first reactant it was 0.0020, also raised to the power A. So we're just getting the data of experiment 1 and 3 and then substituting in the equation of our electron. Okay, if we're going to put the other parts for the other two remaining reactants, they are all going to be of the same data and they're going to divide. Okay, as you can see they are the same, so no need of us showing them there. If you want you can show them, no problem. So if we're going to divide 4.8 by 2.4, it's going to be a 2. The k's will subtract. Since we've got the same power there, if we divide what's in the brackets, we're going to get a 2. We'll maintain the power. So therefore, A automatically becomes a 1. So we found A is equal to 1. So we can now take another step and try to find the values of other letters as well. So experiment 1 and 3 has already worked. Let's try to identify some other experiments that may help us. So if we look at 2 and 3, first one is the same, third one changes. So we're going to now find iodide. So how do we go about it? So equally we substitute in the same equation. Which one's got bigger values? 2 has got bigger values. So 5.0 as the rate times 10 to the power negative 4. And then a constant K. So this one is the same and hydroxide is the same. So we'll leave them out. Focus on the iodide, which was 0.0040 raised to the power what? B divided by the second the third experiment. The value becomes 2.4 times 10 to the power negative 4 equal to K. For the iodide there it was 0.0020. The power B as well. So what do we have? So 5.0 divided by 2.4. So we're going to have 2.0833 equal to K will cancel out, and then 0.0040 divided by that is going to give us a 2. Since the power is the same, we'll maintain it. So we're not interested in those values. Okay. So therefore B becomes 1. So B is equal to 1. Try to identify the others as well, where the other two are going to be constant, and then find the power of the hydroxide. So which experiment do we have this reactant and that reactant the same, and then the other guy is different? Try to pay attention, try to observe. So it's actually 3 and 4. These two are the same. That is unique. Okay, so starting with the fourth experiment, we have 4.6 times 10 to the power negative 4 equal to, so I'll ignore the first one and the second one, and then I'll go to hydroxide. Hydroxide at 1.00 to the power C over 2.4 times 10 to the power negative 4 is equal to K, and then of course we're dividing by, is it 0.50 the power C. So grab whatever you have, grab what you have, and then try to divide. So let's be careful what we've done here. What have we done? So the first experiment that we've put on top is fourth experiment. So 4.6, 0.5. So I've actually swapped there. There it was supposed to be 0.50, and then at the bottom you have 1.00. So 4.6 divided by 2.4 is going to give us 1.917 is equal to, K will cancel out, 0.5 divided by 1 is going to be what? 0.5 over 1. 0.5 there it's a 1, there it's going to be a 2. So we have 1 over 2. That's the power C. Now I said 1 over 2 is the same as 2 to the power negative 1. So 1.9, we want to deal with all numbers here. So let's take that as a 2, considering experimental errors. And then that will be 2 to the power negative C. So negative C can be equated to 1. And then C becomes negative 1. So C therefore is equal to negative 1. So therefore, the lateral becomes R is equal to K, first reactant OCl negative, raised to the power 1, iodide to the power 1, and then hydroxide to the power negative 1 can be on the bottom with a positive power. So this is our lateral. What is the overall order of the reaction? Was also a question that we needed to answer. Determine the order of the reaction with respect to the reactants, and then the overall order. The overall order requires you to add 1 plus 1 plus a negative 1, which gives us a 1. That's the overall order of the reaction. What else? We're supposed to find the value of the rate constant. So to find the value of the rate constant, get any experiment of your choice, substitute in the given data that we have. Okay? And then try to find the value. So I can go for experiment 1. Okay? And then I'll plug in the values that we have. So for the rate for the first experiment, we had 4.8 times 10 to the power negative 4 being equal to K. And then you can plug in for the other reactants. So for HCl, it was 0.0040, and then for the iodide it was 0.0020 divided by the hydroxide, which was a 1.00. Okay, so I'll go there is to find the value of K. So let's try to punch all those on the calculator there. 0.0440 times 0.020 divided by 1. Okay, and then we should be able to find the value of K. So the value of K I'm getting is 60. Now the fact that this is the first order reaction the units are second negative. If you are going to plug into our formula for finding the units, it's m1 minus n and then second negative. So n is 1 as overall order, so we just remain with second negative for this part of the question. Now B becomes very interesting in that we are taught to show that the reaction mechanism given below is consistent with the net equation. So let's try to test and see if it's going to be stoichiometrically correct, and let's try to show. So all we do is to add all these steps we have. That's all we do. Cancel what's appearing on the opposite sides. Okay, so let's start. I can see this guy is appearing on opposite sides. I can see hydroxide is appearing on opposite sides. I can see water is appearing on opposite sides. I can see, what else can I see? This guy is also appearing on opposite sides. So what remains on the reactants are only two. So OCl negative plus iodide negative. And then on the right we have Cl negative plus OI. So if you try to observe this one, it's stoichiometrically correct, right? So Cl, so that's correct. Okay, and we can clearly see that all these two reactants we have are basically part of the lateral that we determined. What was our lateral previously, if you saw from the previous question? So our lateral was KOCl negative, iodide, and then of course hydroxide. So we can see that both reactants that have come up are part of the lateral, so which is proves this to be correct actually. Okay, so it's not always going to be necessary that all the reactants are supposed to be in the lateral now. So now there's another segment of the question that we need to focus on, which is determining which one is the rate determining step. And of course, because of the fact that we have to show, so let's be careful. So if we try to observe again our lateral, we can see that we have OCl negative, iodide negative, hydroxide negative. So let's first of all try to determine the laterals in respect to this, because the rate determining step is a slow step. Okay, if you are new to reaction mechanisms, I would recommend you watch a video about that on our site. It's about 1 hour, so you understand the idea of reaction mechanisms. Reaction mechanisms should be able to give you the net equation, should be able to give you the lateral as well. So let's see which guy can give us a lateral. Okay, so we have to come up with the laterals for both the backward and backward reaction for the reactions that have a species appearing in the lateral. So if you look at the first one, for step 1, if we look at the reactants, we can see that the first one is appearing in what? In the lateral. So we're supposed to write the lateral for that one. So lateral for the forward reaction becomes, so we'll write them based on the stoichiometric coefficient. So OCl negative and then water. Are we interested in the backward reaction? If we try to observe, we can see there is hydroxide, which is also part of the lateral, so we can also write it. So for B, for the backward, so that would be HOCl and then hydroxide. And then for, so apparently we're assuming that one to be an equilibrium reaction. Okay, so and then for step 2, for the forward reaction, we can see that iodide is part of the lateral. For the backward reaction, we don't have anything, so we'll only focus on the forward. So our late for step 2 becomes K iodide and then HOCl. By the way, if you had a 2, for example, on water, it would mean the power would be 2. So we are raising this based on the stoichiometric coefficients. And then for step 3, for the reactants, hydroxide is there. So we have to show it. Backward reaction, none of the two are part of the retro, so we can just ignore them. Now, which one is the rate determining step? Is it step 1, 2, and 3? So we can disqualify a few here. The ones having hydroxide in the retro is appearing on the denominator. Now, if you check where it's appearing, it's on top. It's a numerator, so those ones are automatically disqualified. Okay, so disqualified, they can't be the rate determining steps because they're contradicting the retro itself. So we've removed the backward for the first step 1 and also step 3. Now if you check the first one we have OCl minus and water. So this is matching up, but water is not. If you check step 2, iodide is matching up, but HOCl is not. So we have to choose between the two, which one is most likely to be the rate determining step. Now for water, if you check water is there, and then it's also there. But if you check the other reactant, HOCl, we'll notice that it's an intermediate. Just upon it being produced in the first experiment on the first reaction, it's taking part in the reaction in the second one. So that one, at least we can make some changes to it. So most likely step 2 is the rate determining step because it's containing an intermediate, and then one of its reactants is also matching up with the retro there. So don't forget, this is K and then OCl minus. So for the intermediate, we can actually substitute it. We can substitute it with something. That's a good part about intermediate. So where is an intermediate appearing? In the step 1 and also step 3. So let me do something here. So we can actually combine step 1 and step 2. We can first of all focus on step 1. So if we look at step 1, we can combine the backward and the forward by equating them together. So if we equate them, K for the forward, that's for the forward. The backward is K HOCl hydroxide. Our goal is to make the intermediate the subject. What do we end up with? So this is forward, that is backward. So divide by K backward and then hydroxide. So on the right, those ones will divide. So HOCl becomes a subject in that one. Okay. So step 1 has given us an expression for what? It has given us an expression for the HOCl by making it the subject, right? Now, in the assumed rate determining step, we said it's step what? Step 2. Now step 2, the retro for step 2 was what? R is equal to K iodide and then the intermediate HOCl. So we've come up with an expression for HOCl from step 1, so we can substitute in that equation. So if we're going to substitute, we're going to have K iodide. Now on HCOCl, we're going to put this O part. Okay, so let me just move it. There we have it. So all the K's can be multiplied together, they can divide together to form 1K. So this K multiplied by that K divided by this K is just a constant. And then remain with iodide on top. Okay. And then OCl negative over hydroxide on the denominator. Now water Since the concentration of water does not change, can be taken to be a constant and so omitted in the lateral expression. So you notice that actually step 2 is a determining step, in that it has given us a lateral which is matching up with a lateral which we determined experimentally. Okay, so step 2 is the rate determining step. It's a Stroll reaction there. Now C says, is it appropriate to refer to hydroxide as a catalyst in this reaction? Now if you check hydroxide, it's actually part of a denominator. If you're going to increase its concentration, the reaction is going to be, the rate of the reaction is going to be slowed down, because the rate and hydroxide are inversely proportional. If you increase hydroxide, it means the value there will reduce. It's like if you've got R being equal to 1 over X. If X becomes 100, it means that value will reduce. If it becomes less, R will increase. So it is not a catalyst because it doesn't speed up the rate of the reaction. Instead, it slows it down. So we can instead call it an inhibitor instead of it being called a catalyst. Alright, so we're on question 5, which is also given as like the initial rates. Okay, so here the issue is we've been given in terms of pressure. Okay, now pay attention. So listed below are the initial rates expressed in terms of the rate of decrease of partial pressures of the reactant at temperature. Determine the lateral of this reaction, including the value of K. So our goal is to find the lateral and also the value of K. Now, one thing that you're going to see is this table is unique from the tables you've seen so far, in that instead of us searching for the partial pressures of both nitrogen oxide and the hydrogen, what has happened is they've already given us a part which is having them constant, right? So you can actually extend every part of this table for easy understanding. So in this case, on the left, we are told the initial partial pressure of, so say partial pressure of hydrogen was like 400 millimeters of mercury. So it was constant throughout. That's the implication. And then on the other side, it means as well for nitrogen oxide, it was like constant throughout. Yeah, it was also 400. So this table is separated into two. Each part is having the partial pressure and also the rate. So to determine, of course, the reaction order in respect to nitrogen oxide, we can get any two of our choice. Okay, any two of our choice. So if I look at the values that we have for the rates, what do we have? We have 0.5, 0.750, 0.515, and 0.125. So the ones that I believe can give us a better number in terms of division is these two. So I'll go for 3 and 2. And then the one having a bigger value is rate 2. So our lateral in this case can be expressed in terms of the reactants we have. So our rate is K. The reactants, we had nitrogen oxide and then hydrogen. Can use powers M and N for the two. So for the very first one, our rate 2, okay, will be divided by rate 3. So for the second one, the values we have 300 and 0.515. So substituting in that equation, our rate was 0.515 equal to constant K. For the nitrogen oxide, here we have it, that was 300. The power at M. For hydrogen, it was constant, 400. So the power N divided by, now divide by the third one, the rate there was 0.125 equal to K. And then of course Of course, these are the cases where let me even try to be careful in terms of where let me remove a cosine there, but know that that's what actually is happening. So K, and then that is like 152, okay, the power m, and then we know that our hydrogen was constant at the constant partial pressure. So at this point, these would divide, and then on the left, 0.515 divided by 0.125, approximately value is 4.12, and then we're going to remain the K's will also divide. We'll remain with 300 over 152. So approximately the value is like 1.97. Of course, with the same power m, so it's approximately 1.97 the power m. So what remains of it is becomes 4.12 is equal to 1.97 m. We know we can round it off to a 2, right? So 4 is equal to 2 power m, and then that can be 2 to the power 2 is equal to 2 to the power m, and m becomes 2. Okay. Very simple and straightforward. So equally, as we observe on the other side of a table, we can get any of our choices. So which ones do you think will make more sense when it comes to division? And we can get any values, but I'll go for the first one and the third one. So my rate there for the first one was 0.800 is equal to K. Nitrogen oxide is one that was constant, in this case 400 to the power m, and then hydrogen was like 289 to the power n. So divide by the third one, so that would be 0.395 K, so 147. No, it's not 1, this one was constant here, 400 to the power m, and then the one which is changing is the hydrogen, 147 to the power n. So things that would divide, K and the 400 to the power m would divide. Now 0.8 divided by 0.395, approximately 2.03. Okay, 0.8 divided by 0.395, approximately 2.03, and then on the other side 289 divided by 147, approximately 1.97 the power n. So 1.97 can be just considered to be a 2, so that n essentially is also 1, right? Due to experimental errors. That's why there may be such minimal differences. So we found the reaction orders in respect to both reactants using the data given in the table there. So if we're going to write our lateral will be R is equal to K. In respect to nitrogen oxide, the power m was found to be 2. In respect to hydrogen, it was found to be 1. So we found the lateral. Now we have to find the value of K. Okay. So usually in this kind of questions, what I want you to do is I want you to find the value of K for every point, every experiment. Okay, what do I mean by that? So they want you to look at the first line there, plug in the values you have, find the value of K. What do I mean? What I mean is, let's create an extra column for K. Remember, this table is like split into 2, but it's the same table. We can extend it to be 1. So I want you to find the values of K for every row. So you know you find the value of K by actually substituting, right? By substituting. So if I'm going to go for the very first one, I know my rate there was 0.750 is equal to, and then K. Now if you make K the subject of a formula to make things faster, you'd notice that you'll be dividing by the nitrogen squared. So let's make K the subject of a formula. So divide K, make it the subject, you end up with the rate. divided by the nitrogen squared and then the hydrogen. So we'll just be plugging in. So for the first one, the rate there was 0.750 divided by nitrogen dioxide was 359, hydrogen was constant to be 400. So I'll grab my calculator there. So 0.750 divided by 392 squared multiplied by 400. Okay, so the value of K I'm getting here is like 1.22 times 10 to the power negative 8. If I go for the next one, the rate here it became 0.515. The nitrogen dioxide became 300. And then we know it was constant for the other part. So let me punch that on the calculator. 0.515 divided by 300 squared times 400. So 1.43 times 10 to the power negative 8. So I've seen that these values are close. And then if I'm going to go for a third one, can make some changes. The rate there was 0.125, and then the partial pressure was 152. So 0.125 and then 152 squared. So here we have a value of 1.3235. 1.35 times 10 to the power negative 8 as well. If we cross to the other side as well and begin doing the same, what you'll notice is on the other side things will change, will swap. So what will become constant is now the nitrogen, which is now 400 squared, and then everything else will be changing. On top, the rate for the first one was 0.800. So, and then the hydrogen partial pressure was 289. So 0.800 divided by 400 squared times 289. So I'm getting a value of 1.73 times 10 to the power negative 8. What else? 0.550 for the next one, and then 205. So 0.550, 400 squared, 205. So 1.67 times 10 to the power negative 8. And then for the last one, that will be 0.395. So 0.395 and then 147. So 0.395, 147, 147. So 1.68 times 10 to the power negative 8. So that's how you find the different K values for all these. So this is why I say you only do this if you've got enough time. In the cases where you don't have enough time, just approximate the value of K by using just one step, right? So therefore, you can add all these and then just like try to come up with a average value. After you add 6 of each values, divide by 6. What you're going to get is the average value of your K. Yeah. So approximately to be in the same range. So let me just try to add them. I'll ignore the 10 to the power negative 8. I'll just get the 1.22 plus 1.43 plus 1.35 plus 1.73 plus 1.67 plus 1.68, and then of course that's times 10 to the power negative 8 divided by 6, since that's in the R. So the value I'm getting for K is 1.513 times 10 to the power negative 8. For the values of units of K, I said use a formula 1 minus n, second negative, where n denotes the overall order. In this case, the powers 2 plus 1 gives us a 3. So which would be equal to m minus 2 second negative. So these are the units for value of K in this case. Also, if we look at question 6, here we are told given the following observations, experiment 1, experiment 2, and then experiment 3. So we've been given the values in respect to reactant A and B, and then also the initial rates. Now, the statement continues to say the reaction between A and B is first order, okay, in terms of A, and 0 in terms of B. So if we're going to come up with a lateral expression, our rate is going to be expressed as K, and then in respect to A, we are told it's first order, so the power 1, and then to B, the power 0. So this basically just is going to remain as R is equal to K, and then B does not have an effect on the rate since it is raised to the power 0, which implies every time it doesn't matter the value there, it will always be a 1. So this is our lateral. Now, for us to find the values of x and y, how do we go about it? So it means we're trying to find the value of R and A respectively. Okay? Now, we have to look at experiment 1 because in experiment 1, all the values are known. So we can therefore find the value of K. So let's substitute. So for experiment 1, the initial rate was 2 times 10 to the power negative 2. The value of K we don't know. The value of A, which is the concentration, was 0.1. So divide by 0.1 on both sides, 0.1, 0.1. So here you notice that the value of K is going to be 0.2. Okay. Now, if you look at the units we have in this case, the concentration is mole per liter, which is the same as molar concentration, and then the time was in minutes. Now, the value of K, you know that the units can be expressed in terms of what? So for the first order, the units is just going to be time negative. So in this case, it will be minute negative. Okay, so we found the value of K, which is going to be very useful. So the value of K can be shown in the equation to be 0.2, and then we remain with our A and our R. So if you look at now 2, where they want us to find the value of x, you notice that x is representing the concentration of A. So R is equal to, R was given in that case to be 4 times 10 to the power negative 2, and then we're trying to find x, which is representing A. So divide both sides by 0.2, 0.2. You notice that the value of x essentially becomes 0.2. Now, what is concentration? So molar concentration, or mole per liter if you want. So that's the value of x. For the value of y, it is actually the rate, as you can see. So we're trying to find R. I'll put y, 0.2, our A, or 0.4 there. So y is equal to 0.2 times 0.4, 0.08. So what is the rate? So it's molar concentration minute, right? Molar concentration per minute. Now notice that in this case, we've not used any value of B. Why? Because it is not part of the lateral overall, because you raise the power 0, so its values has got no effect in any of the calculations we've made so far. Okay, that's very important. Question 7. Consider the reaction of nitrogen dioxide with fluorine to give nitric fluoride. How is the rate of formation related to the rate of reaction of fluorine? So very simple. We're focusing on fluorine and the formation of that. So I told you that if you want to come up with the rate, the formula of the rate, it's the change in concentration over change in time, of course, multiplied by 1 over the stoichiometric coefficient. So if I'm going to look at fluorine, it will be negative of 1 over 1 change in the concentration of fluorine over the change in time. That should be equal to the change, so of course 1 over 2, and then change in concentration of the nitric fluoride, which is like formed, over change in time. So that is like, this is like the rate of formation, this is like the rate of consumption or the rate of reaction of fluorine. So at the end of it all, if you are going to give you values for fluorine and nitric fluoride, you should be able to attain the same rate value. Now, so we can equate the two to find the relationship that exists there. So we know that for the sake of our calculations, all values are going to be positive at the end of it, all right? So let me ignore the negative, and then we can have fluorine and then change in time. So that alpha is there, we can multiply both sides by 2. So the 2 will appear on this side, and then you have the rate of nitric fluoride formation being equal to that. So the conclusion here is the rate of formation of nitric fluoride is twice the rate of reaction of what? Fluorine. As we can see, it's twice the rate of the reaction of fluorine. That's the basic idea for question 7. Now question 8, here we are taught to determine the percent of H2O2 that decomposes in the time using the value of K to be that. Okay, so be smart about it. If you look at the value of K, the units are second negative. So second negative or time negative, just know that it's a first order reaction. Okay, now in this case this is decomposition, so decay is a first order reaction. So here you can also use the value of K to determine the rate of the reaction, the order of the reaction. So we are told that determine the percent that decomposes in the time using K is equal to that. So the time for the concentration to decompose is 600 seconds, and then also again for 50 seconds. So we've got two parts of the question. We have to determine the percent that decomposes in the time using that. Now if you look at the value, if you look at the integrated ratios, an integrated ratio is the only equation that combines the value of K, time, and the concentration. So it's a natural log of the final concentration being equal to negative KT plus the natural log of the initial concentration. Now if you're going to bring the final and the initial on both sides, it become a minus. Now if you've done your logs, you know that when you're subtracting two logs with the same bases, you can combine the log and then divide the values. So you end up with A final over A initial being equal to negative KT. Now we want to do away with the natural log. So you can introduce the inverse, which is E, exponential on both sides, right? E. So you know that all these are going to be raised to the power E, if you introduce the E, right? So you notice that where there's a natural log, it remains as it is. Since they are inverses, they'll just cancel out. And then on the right, since there is no natural log, it automatically becomes the power, negative kt. So this is another form of a first order reaction that can be useful in this kind of a question. Phi over A initial is equal to E to the power negative kt. So for the very first part, since we want to determine the percent, this is better in that this is already giving us a fraction or a ratio. So it's better off final in respect to what we started with. Okay? So all we just have to do is just substitute on the other side. So for the 600 seconds, the ratio of the final to the initial is obviously going to be equal to E to the power negative k. K was obviously 6.40 times 10 to the power negative 5. And then multiply by the time. The time there is 600 seconds. Don't forget you have second, negative, and second, so we are going to cancel out. So 600. So when you plug in those values, the value you're getting is 0.9629. Okay, so that's the value. That's the ratio of the final to the initial. So what does that mean? So you found the ratio of the final to the initial. So now in this case, I want you to focus on the percentage. Okay, the percentage of what? The percentage that decomposes. If you look at the ratio of the final and the initial, let's say if you add 10 and then it decomposes to 4. Okay, or let me not say decomposes to 4. Let's say you add 10 and then what remains after decomposition is a 4. It means this is your final, that is your initial. And what that means is you have got 4 over 10 final over the initial. This percentage is what has remained, not what has decomposed. So to find what has decomposed, first of all find the percentage of what has remained and then you subtract from what was available initially. So in this case what we found is a ratio of what has remained in respect to what was there at start. So this is not what had decomposed, but this is what has remained. So we can express it in terms of a percentage by multiplying by 100. So multiply that value by 100 times 100. So it's like final over initial times 100, which gives us 96.29, which I can summarize to be 0.3%. This is how much at what remained, because it is final over the initial. Now to find how much had decomposed, you have to find the difference. So subtract from 100 how much had remained to determine how much had decomposed. So you end up with a value of the 3.71% to have decomposed in this case. Same concept can be applied to the different time of the 400 seconds. Okay, so you can find the ratio of the final to what had remained initially. So you will notice that the value is 0.9720, okay, times 100. To get a percentage, it becomes 97.2%. This is how much had remained. Equal, you can subtract from 100 to determine how much had decomposed. So you find that it's 2.8% in this case. So that's how you handle question 8. You are easily able to come up with the ratio of the final to the initial by expressing the equation in the form of an exponential using the natural log equation. That is for the first order integrated equation for the first order reaction. Now we're on question 9 and 10, which are very simple and straightforward. So if you look at question 9 we are told bromide ion is oxidized by bromate ion in acidic solution. The experimentally determined electron is that. So we've been given the electron. What is the order of the reaction with respect to each reactant species? So the powers are basically the order. So that is 1, that is 1, that is 2. So in respect to the first reactant, the order is 1, second one 1, hydrogen 2. So those are the reaction orders. What is the overall order of the reaction? So you add all the reaction orders. 1 plus 1 plus 2, so 4. Question 10. What are the reaction orders with respect to each reactant species for the following reaction? Okay, so here we are given the electro is that. So our electro is K, and then dependent on nitrogen dioxide 2. So the other one is not appearing, the other reactant is not appearing, so obviously it's the power 0, so it's 0, and then the other one is a 2. What is the overall order? Overall order is 2 plus 0, which is just 2. So overall order is a 2 for question 10. Question 11 is our next question. The initial rate method was applied to the decomposition of nitrogen dioxide, as we can see. And then here we are told it yielded the following results. So we've got the initial, and then you've got the initial concentration, and then you've got also the initial rate of concentration formation of one of our products, oxygen. So in short, you've got the rate and the concentration for experiment 1 and 2. So find the rate law and the value of the rate constant with respect to oxygen. Okay, now if you observe this question, starting from this side going this side is a different question, because what does it say? The composition of is first order, so it's a different question. So let us read them. So for the very first part, ignore this. So we have to find the rate law in this case. So our rate law R can be expressed as K. We only add a single reactant in this case, so we can say let it be raised to the power X. Okay. So to access the solutions to question 11 all the way up to question 19, so question 11 is there, 12, you can see all the way up to 19. All these questions have been answered. So register, the link is in the description, go to our site. You can also check them out on Patreon. So you learn the topic in detail, and then you also have access full solutions to all these questions.